Okay, last one. What I'm going to do now is the last problem, which is the marble in the bowl problem. So here's the bowl, my crappy bowl, with a radius, let's say, of, we're going to say the bowl's radius is capital R. I think this is normal this is what was the problem did. Now the trick is that we've got, let's see, I'll use red for this. Okay, we've got the ball rolling around a circle, okay, in the tape or on the side of the bowl. So some way up the spherical bowl, it's rolling around a circle, and the angle that you make if you draw like a line from the circle that the ball is moving into the center of the bowl, the angle that makes with vertical is theta. Okay, so the ball is going around at this angle theta, and let's see. Let me draw maybe drawing the top of the bowl will clarify things. Okay, so this is sort of a side view of the bowl. So the question is, really, we're forcing it to do this by sort of gently swirling the bowl with an angular velocity of omega. Okay, and you can try this if you have a spherical bowl and a ball of some kind. You just put the ball in the bowl, and the bowl doesn't even have to be perfectly spherical. If it's got sort of a flattened bottom, like a lot of food bowls or whatever, that'll work fine. You just sort of swirl around gently at omega, and the ball will start rolling around the inside of the bowl. And if you keep omega constant, it will actually stay at a constant level. Of course, if you change omega, I think intuitively can see if we increase omega faster and faster, the ball will rise up the side of the bowl. Okay, and if you go slower, it should lower down. So the questions are, I think we had to find omega given. No, I'm sorry, not that. The other way around. Find theta given omega, and then investigate like whether there's a maximum or minimum value of omega. So to find this, what we do first of all is we use our standard A equals A, which means you take an acceleration you get from FBDs and forces, and you set that equal to an acceleration you get from uniform circular motion kinematics. Okay, so with regard to the FBD, the marble, or whatever it is on the side of the bowl. We'll call it mass of M. And let's see, when theta is 0, we're down at the bottom here, and it'll be a flat slope. And then as theta increases, it gets to be a steeper and steeper slope. So actually, theta is this angle here, okay? And I'm going to do an FBD of the ball like this, and we're going to have, okay, there's mg. We're going to have a normal force, and that's going to be it. And the normal force is going to make an angle theta with vertical. And what you'll find, in fact, is that this is a standard bank turn problem. Okay, so we need to accelerate this way because the center of the circle is sideways from where the ball is. And so you're going to need to use your standard coordinates. And I'm going to skip this because I think, this has been done before. You should know how to do it. If not, this is the standard treatment of a frictionless. In fact, even if you haven't done it before, I've given you enough here, really, to do it yourself. Okay, so I'm going to, not quite E. So I'm going to say this is the standard frictionless banked turn derivation. Do it if you want. Don't do it if you want. But what it leads to is the acceleration of the ball is going to be equal to g tan theta. Oops, sorry. G tan theta. So now, what do we want to do? Well, we got omega. So for my UCM side, I'm going to use omega squared r equals A. Okay, A equals omega squared r. That's one of your two probably most important centripetal acceleration equations. Okay, and then on the other side, you're going to have this, which is going to be G tan theta. So now, whoops. Okay, so there we go. Now, one little trick here. I used a lowercase r here. How is that different from uppercase r? Well, it is different because lowercase r is the radius of the circle, and uppercase r is the radius of the bowl. So if we look at this little triangle here, this black dotted line I drew here is lowercase r, okay? And this hypotenuse here is uppercase R. And this angle is theta, right? So if we want to draw that triangle out, okay, this is capital R, the radius of the spherical bowl. This is lowercase r, the radius of the circle, and this is theta, which means little r, let's see, is going to be big R times sine theta. Okay, so plugging that into here, we're going to get omega squared, and then little r is big R sine theta, which is going to be equal to g times tangent of theta. Of course, what tangent of theta really is sine theta over cosine theta. So what you're going to get is your sine thetas are going to cancel out. And let's see, we want to find theta given omega, right? So what I'm going to do is cancel those. I'm going to bring the cosine over. Well, hold on, I'm just going to do it like this, okay? So omega squared r equals g over cosine theta. So now I'm going to multiply the cosine theta over, bring this underneath, and get cosine theta equals g over omega squared r. And now theta is going to be inverse cosine of g over omega squared r. Okay, so, sorry, excuse me. So, what are the limits on theta, and what are the limits on, actually what we really want to find is what are the maximum and minimum omega that make this work, okay? So, cosine of theta, cosine can range between 0 and 1. So, you've got to look at what that means for our values of theta. So, to get theta equal to 0 degrees, then we need cosine of theta has to be equal to 1, right? Okay, which means this in here has to be 1. Okay, so to get have the ball sort of hanging around at the bottom of the bowl, doing these very tiny little circles, this is what we have to have. We have to have this in here equal to 1, so that theta equals 1. Sorry, so that theta equals 0. So g over omega squared r equals 1. And so this is kind of interesting because what this gives you is omega squared equals, let's see how this works, g over r, or omega equals square root of g over r. And it turns out if you think this through, you'll realize this is a minimum value for omega. So if you want to swirl the bowl, if you do it really slowly, the ball will just sit at the bottom of the bowl and do nothing. Okay, you have to exceed this square root g over r. I've got a bowl I use in the classroom to demonstrate. Well, I've got the top of the Van de Graaff generator. So Van de Graaff generator is that big circular, the big metal sphere with the column, and then it sparks and shocks people. So what I've got is the top of one of those, because it comes in two pieces that sort of snap together. So I take the top off, and there's a nice spherical bowl. I put a little steel ball bearing inside, and I can swish it around. And it turns out there, you have to swish it at least like with a frequency of like 1.5 little circles per second. So if I'm going really slow, like watch my mouse cursor, okay? If I'm going like this, that's too slow because that's like 1 cycle per second, and the ball doesn't move. I have to be going like about this fast to get the ball to do anything, okay? So this is a minimum value of omega. Beyond that, the ball there's not enough excitement, I guess, for the ball. I suppose I really haven't we haven't learned enough to actually say physically and really describe it well why this is true, but mathematically you can see at least that when you go too slow, the ball will just sit at the bottom, and that kind of intuitively makes sense, okay? Now we're going to look at the other extreme. Theta equals 90 degrees, okay? Well, that means, everything over here is the minimum. So that means cosine theta equals, well, what's the cosine of 90 degrees? 0. So that means we need to get g over omega squared r equal to 0. Well, now that's going to be kind of hard, okay, because g and r are constants, okay? So what this really means, g is, gravity, and r is the radius of your bowl. You can't change those. So what this really means is you need 1 over omega squared needs to be 0. Okay, which means then omega squared needs to be equal to infinity. And so what this means, and this seems kind of odd, what this means is you can swirl this bowl as fast as you want. And if you're holding it perfectly level and swirling it smoothly, really just moving in circles, the ball will ride higher and higher up the bowl as your omega goes up, but it will never actually get to the edge, assuming the ball is a point mass and you don't jitter it at all. It'll never actually get to the edge. So when you're going sort of infinitely fast, it'll be right up there at the corner, but you will never, with any finite value of omega, get it to go over. And that seems kind of strange, but it's true. And you can try it with your own bowl. You will have the ball pop out, of course, but that's because you either sort of jerked it around and did some unsmooth swirling, or maybe because you jerked it vertically, or maybe because your bowl was slightly tilted or whatever. But in principle, there's no upper limit. So there's a minimum omega like this. If you don't go above that, it stays at the bottom of the bowl. And there is, no maximum on omega, okay? In principle, in theory. Okay, so there you go. That's all you want to know about swirling a ball in a bowl.